So welcome to the session, sir.
Thank you, madam.
Very energetic sessions actually. It's been third session continuous and they're very useful also. So the platform is yours. So you can start the session.
Yes, madam. Definitely. Thank you.
Yes, sir. Thank you.
Good morning, all of you. So today we're going to discuss about the vibration analysis of smart materials and the structures. Madam, can I start?
Sir, yes, sir. You please start.
Yeah. Okay. Thank you. Thank you, madam. Then, majorly we are going to see the retrospective view of how the materials have changed. Or just I won't go much deeper. Majorly our focus is on smart materials and vibration analysis. So the basic need, maybe we are not I am not going for these stonies and all. Just we can say like civilization started once the pure metals. We got these pure metals, and where these pure metals strength is the issue, we use these only for the limited uses. And then there is one technology where we understood we can combine some of other materials to these metals, and then we can enrich its properties. So that's what is called the alloys. So once the alloys have came, the usage of metals have increased dramatically, or there's exponentially increased its usage. Then that's called the very highly we have usage of these alloys. And there, then we saw like, okay, the weight is a issue, and then fabrication perspectives. So many things have came into the picture. So then why don't we go with some material where there could be some high performance materials, then refractory materials, ceramics, then plastics have came. The ceramics, due to its the brittleness or other properties, it is limited only for a particular specific applications. And next one is the plastics. The plastic, due to its durability and its strength, where we can use for a, and not like a very high, or the where there is a high strength is needed, and there we could not use, whereas the low strength places and the low load applications we can use these plastics. So still we are using these plastics. It's but application perspective, we can't say too much of it occupied like anything. In the engineering perspective, I'm saying. Then next one is the composite materials. These composite materials, yeah, when compared with other metals, due to the specific properties, it have a very high applications, and with the less weight we can get a more strength and the stiffness properties and all. So that's why we gone with the composites, occupied a lot of space here. And then now we are searching for a smart material. These smart materials, where it can change its properties by the some excitation, or by external stimuli, or without some external stimuli, where it can have its own properties. They can change its characteristics. So like this way, there is a smart materials having a larger classification. So this what now emerging area is the smart materials. The smart material doesn't mean that only a smart material we are using for a independently. No, it is combined with some composite structures, and these one then it became a smart structures. So now major our topic is the what are the smart materials, and which are used in the mechanical perspective and in the engineering perspective. Then what are the structures? So then how its vibration characteristics can be understood. So that's what the major agenda for this session. First, we'll see the aerospace application where we can observe various things here, various application perspective. Here, if you see, there is a you can completely see here in the vibration perspective where these wings and these places where there is a lot of scope for the sorry, lot of scope for the vibrations. So here these wings and these tail portion, and here majorly only a strength is needed here. Again, here these there is some more forces are being active, though there the impact loads are more, and here the vibration loads are the more, and here also the same. Where there is a some flattering actions or the flapping actions are there, and there the vibration strength or the structural strength you need to be more. So there we are using the mostly the glass fibers, and then we are using these graphite as well as the carbon, and for normal strength perspective we are using the uh, carbon and all. But for where there is a vibration behavior, then we are using a glass fibers. So then aircraft performance increase, like in the again the you can see various analytical methods in the mathematical perspective I'm talking. So where here the theoretical models, their description or the description phenomena and analytical methods and aeroelastic tailorings or by using the composite materials. Now we are using these states called the active materials, and again we are moving towards the application of the smart materials. In this, the active materials majorly to suppress its vibrations, but where the smart materials here it can um, stimulate with or without external stimuli, how we can able to change its enhance its properties. That is the major. Yeah, these working area is a still this research area is still emerging. So then we'll see the what are these smart materials are also responsive materials. The design material that are one or more properties or its state can be changed by some external stimuli. Sometimes there is a without any external stimuli. So what are these various characteristics or nothing but a, or let's say we talk about the vibration perspective, it's natural frequencies and mode shapes and damping characteristics. So once they change its state automatically or obviously there is a lot of change in its vibration characteristics. So what could be the various stimuli? So external stimuli could be a stresses, moisture and pressure, electric or magnetic fields, light, temperature, pH or the chemical compounds. But majorly I'm focusing on the where there is engineering most applications. So these are the three types of the materials, where piezoelectric material and multi-phase materials and the shape memory materials. So the first we will see the piezoelectric materials or the produce a voltage when stressed, and in the vice versa also. If you stress, then it can give you voltage. That is also possible. Then multi-phase materials by giving certain external stimuli, maybe electric field. Then in this case, electrorheological materials where it can change, alter its states, and whereas magnetoroheological materials by applying a external magnetic field, so its properties can be enhanced. And then shape memory materials. Here the shape memory alloys are there, shape memory polymers are there. They majorly working on the large deformation induced and the breakout through the temperature changes or the stress changes. So they can remember their shape, and it can again alter its shapes. So that's what the major the shape memory alloys. Uh, in the shape memory alloys, what are the applications and how various all these three piezoelectric materials, phase materials and the shape memory materials, what are the working principles and how its properties can be enhanced. what are the applications we'll see. And photovoltaic materials or the optoelectronic convert high light to the electrical current. So these are majorly used in the some sensor applications, and then in some chemical applications. The pH sensitivity polymers, then they are majorly in the chemical engineering applications. So there's many materials are there in the smart materials. Other than these, they are majorly used in the chemical engineering purposes and the bioengineering, where there is a drug delivery systems and drug passes and so on. These in the biomaterials applications we are using. So those materials I am not covering. Basically, I am emphasizing on these three types of the material. And as frankly, there is a vibration analysis point of view, only the multi-phase materials vibration analysis. Then we'll majorly see the electroactive polymers. These are the change their volume by voltage or the they are nothing but electrorheological fluids, electrorheological elastomers, bacterioological fluids, bacterioological elastomers. So first we'll see the introduction for the piezoelectric materials. So these are the various piezoelectric materials which are available in the nature. And after processing, we can use these in our real-time applications. Sugarcane, DNA, dental, enamel, and majorly the quartz is the first smart material. Topaz and sugarcane. Sugarcanes are not being explored much. What are the various types of the piezoelectric materials? They are the piezoelectric materials, signal crystals, quartz and lithium, niobate, and Rochelle salt, and then ceramic perspective, lead genoconic type of barium and there is a polymers, celluloses are there, and then polymer composites are a nano composites. So they are also covered in this category. So the piezoelectric materials we are applying in the I already told that actuation and the sensing perspective, where the applied mechanical stress, if you apply a mechanical stress, then it can be a so where there is a actuation perspective, and then here the induced mechanical strain giving some sensing. So this is a sensing. Like this way we can use on the reverse manner also, where we can apply the mechanical field and then voltage signal will come. Where there is a voltage we can apply, then the mechanical signals will come. So these way we have a both types, sensing and the actuation and the sensing devices. Where this one is the actuation and this is a sensing. Sensing is here. So sensing can be here, and then this is the actuation. Where in the actuation, if you give electrical field, it will give a forces to that. So normally this application perspective is a piezoelectric materials patches will be kept on a different structures, and it can be excited as actuation. Then we can apply various forces on these, so we can alter its excitations. So that's a actuation purpose perspective. The same thing if you reversely apply or put a patch in the opposite direction and apply the forces in the opposite direction to its excitation. So then obviously it will control its motion. So that's why the piezoelectric material or piezoelectric patches can be used for the vibration control. Then what are the various applications? We have various applications like nano wires, then nano wires. These are these nano wires we can use inside these heart as well as shoe absorption materials. So like this way we can like here one is a normal application and another one is the medical application, biomaterial applications. So like this way we can use these piezoelectric materials for a various applications. Then next is a shape memory materials. We have a various classification of a shape memory materials. the stimulus responsive materials, so called physical properties, uh, can be remembered like it is a memory type, and another one is called instant and the spontaneous type. So this is called shape change materials. And memory type is called the shape memory materials. And here the shape memory materials we have many: the shape memory alloys, shape memory polymers, shape memory hybrid, and shape memory ceramics, shape memory gel. So these are the various materials. Here the shape memory materials mostly now emerging area is in the 3D printing and the 4D printing area only. And they can be used in the vibration perspective or vibration control perspective. Is having some limitation here, but its major work now presently is going on in a fabrication perspective, fabrication of these shape memory alloys or the shape memory materials. Then next type is the electrorheological fluids. So here we can observe the electrorheological fluids. It will be dispersed in a initial stage. Once we apply a certain magnetic field, obviously it will form a some aligned one, and so that it can oppose whatever the forces are applied, and its strength can be improved. Like till now it is behave like a fluid, and once we apply electric field it will behave like a solid. So then once we apply the more electric field, then it forms like a complete solid. So in this way we can improve, or here we can change that, or we can see that complete state is changing from a normal fluid to the solid. So these are the same images where this we can see these images. So here it is dispersed, and here these are the aligned in a proper manner. So here we completely can see like a solid. So that's how these are the changing its phase. So from liquid state to the solid state. What are these negative electric fields also is possible here, so that we can make these electro rotations, and electro migrations also is possible. So this is one application where we can use these electric rheological fluids in an opposite manner also. Then these are the various applications: electro rheological fluid, engine mounts, as well as the clutch or the brake cases, shock absorbers, and the valves. So here the major electrorheological fluids as well as the elastomer. What the drawback is, we need more high electric voltage. So that is the major constraint here in the electrorheological fluids or the electrorheological materials. So to overcome these one, there is one more rheological fluid has been called as the magnetoroheological fluid, where here when compared with the electric field, the magnetic field requirement is very low. And here you can see this stress strain diagram also. It will go with a mostly in the plastic stage. So here also the same concept will be there, where the state can be changed. So you can observe here there is no magnetic field. It acts like a fluid, and then once we apply a magnetic field, these iron particles. So majorly here, the what are these particles? So here also and here also is these are the electrorheological fluid particles. This one here, these are the magnetoroheological fluid will have these iron particles. These are the ferrous particles. Ferrous particles here. Once you apply a magnetic field, these iron particles will come to the alignment, and after a complete application of a magnetic field, then it behaves like a complete solid. So what are the shortcomings of these fluids is a accumulation and costly, then deposition and environmental contamination and sealing. These are the various problems related with the microbiological fluids. And though when compared with the electrorheological fluids, definitely they are the advantages in the position. So these are the next type is a microbiological elastomer. there also will have a iron particles. These iron particles are not immersed in a fluid, but here immersed in a rubber. So this is a one same image before applying the magnetic field and after applying. Here majorly telling like how it works. So these are particles, and we can have a matrix. So if you take these as a bacteriological elastomer, this matrix will be a rubber elastomer. Or if in the case of a fluid, bacteriological fluid, it will be a fluid. So this fluid and the iron particles will become and then mixing with some additives based on the requirement and curing with no magnetic field. If you don't use any magnetic field while curing, then it is called as the isotropic MREs, and curing with the magnetic field, it's called the anisotropic MREs. Whereas here in the macrorheological fluids, with these the procedure will be stopped. Whereas MRE, there is a few more steps are there, or one more step is there. If it is for the isotropic MRE and the anisotropic MRE. Whereas in the macrorheological fluid, there is no chance that anisotropic or the isotropic. It's completely the isotropic only. So then once you apply the magnetic field, then it will come to the alignment. So whereas here that alignment we can fix in the starting stage itself where anisotropic MREs. But the constraint here to make these anisotropic MREs are the applying the magnetic field at a fabrication stage is a one difficulty in the context of how to keep this one arranging the magnetic field. Then one more thing is for the larger area, providing the magnetic field is also a one more challenging task. So due to these two challenges, the anisotropic MREs are not uh, having more applications or the more fabrication here. But whereas the isotropic MREs, where the cost is also very less, not to provide any magnetic field. And one more thing is in the anisotropic MREs, there's a cost effect. Cost is a more. So due to these, most of the MREs we can see as a isotropic macrorheological elastomers. Macrorheological elastomer, which operate, as I already told, macrorheological fluids will operate in the plastic stage, but whereas it operate in the macrorheological elastomers, the pre-yield region. Linear viscoelastic strain will be 10 percentage. So whereas this MR fluid in the pre-yield region only a 0.1 percentage of its elastic viscoelastic properties. But whereas remaining 99.1 will be done in the only the plastic stage. So that's why the macrorheological elastomer, even though it is contained with the combined with a rubber, so it won't get affected its performance of a due to the shearing of a rubber particles. So it won't be there because of this electric strain. Mostly it is under the pre-yield region. Then operating temperatures is a one thing where minus 50 degrees centigrade to 150 degrees centigrade and cheaper compared to the MR fluids. That is the major advantage here. So if you go for the anisotropic, there is some more costlier, and compared with the isotropic MREs are more easier. Then various applications, the stiffness controlled devices called elastomer bearings, vibration observers, and semi-active vibration control devices, the car suspension, etc. Anyway, these applications we'll see very detailedly. When these are the what are the various working now in the elastomers, as well as the MRF is also the same sort of the applications are there. Here MRE sandwich beams and multi MWCNT, multi-wall carbon nanotube macrorheological elastomer sandwich beams. So this is a new area they design. And next you can see here the cylindrical laminated composite shells. These a panel without CNT. So this is a without CNT and with CNT. So you can observe this carbon multi-wall carbon nanotubes. Without these carbon nanotubes, it is one area where uh, the shell areas till now we have seen only the plates perspective, how it can be vibrating. But in some dome cases and all, where there is a smaller aircrafts and some other structures, shell structures, is subjected to a more wind energies and fluttering actions. There we can use these sandwich magnetoreological elastomer sandwich shells. By applying these magnetoreological elastomer as a its core material, it can increase its stiffness and as well as the damping properties of the shell structure, so that its life will be enhanced. So then here we can see 1 percentage of the weight, the CNT, and 0.5 percentage of CNT and MRE sandwich beams. So those who are working in CNT, mostly they can observe that, they would have known that this 1 percentage of the weight of the CNT will give the best quality or the best properties in their characteristics. Then how these sandwich MRE sandwich plates will be made, where there is a two face sheets are there, and in the middle is the MR material core. And these are the MR material core. And these are about the face sheets in the shell structures. These are the beam cases, and these are plate cases, and these are the shell cases. Like this way, there is a three different structures are available. And now we'll see this vibration analysis of a laminated composite microelastic fluid sandwich plates. So here we can observe these are the composite layers or the composite lamina as a face sheets, N composite layers, and this is the magnetorealistic fluid. Magnetorealistic fluid, actually it should be sealed properly by using a rubber material. Normal rubber will seal then the four sides. Then this is about the composite material. Composite. These both are called as the face sheets, and middle one is a magnetoreological fluid. These face sheets are made of a glass epoxy, glass and the epoxy combination, called the composite laminas. Laminas and combined with the laminate. So as a composite laminate made of a glass is a are the face materials are the face sheets, and middle is the core layer. Then these model analysis testing facility. Actually, we did vibration analysis here. So here you can observe there is a permanent magnets are kept. So the top and the bottom. Actually, not shown exactly here. They are touching here. Touch here. Magnetic material will touch here. So for schematic diagram or block diagram, this is one accelerometer, and there is a 4-channel data acquisition control system. So this is a hammer, impulse hammer, and then the accelerometer, and we both connected with a DAQ, data acquisition control. And by using these one hammer, we are applying a force, the normally the free vibration. Once you apply a force and then take the reading of an accelerometer, take these analog signal, and analog signal will be communicated to the CPU, and these analog signal will be converted to a digital signal by one software called the DV software. So it will convert, the software has been installed here, and it will convert its analog signals into a digital signal, and it will show as how these fast Fourier uh, transform signals will be generated. And here it will, you can understand, or we can observe these natural frequencies as well as the damping ratios. So these are where by altering the change, by altering the distance of the magnetic plates, distance from the face of this surface, by altering these distance, we can change the magnetic field. So obviously, that's how we can alter this zero magnetic field. There is no iron, there is no magnetic plates, and with magnetic field with a large distance then 150, and distance is reduced then 250 Gauss is there, and at these three different positions of the magnetic plates, then we took a readings for the first three natural frequencies have been noted down. And here this is about the boundary condition, where in this boundary condition we can understand only one place. So at this location only we have fixed, and remaining all four directions it is free. And next case is where clamp free. So in the opposite direction one more clamping has been done. So here you can see in the block diagram, then we can apply the forces and then take the reading, and this data acquisition control will convert this analog signal to a we transfer these analog signals here, and then this DV is shown in the fast Fourier transform results. Then we took the three different three first natural frequencies. Then this comparison with the FEM results. For the same thing, we develop a finite element formulation. These finite element formulation I have already shown in the previous class, previous yesterday's lecture. We have discussed about how a composite plate ABD matrix have been, can be derived from for a one plate case. So in the same plate case, how we can apply the finite element formulation to that, and how we can convert these into a MATLAB coding and all. Again, those things we'll see in the afternoon class. Sorry, afternoon discussion. So here it is the measured natural frequency. So from the experimental, and these by doing the analytical simulation. So after these composite ABD matrix generation, and then energy equations are there. These energy equations we can apply various finite element formulation technique, and based on the number of nodes and which element we have taken, that will be converted again in terms of the finite element formulation. Each element, the energy equations, and that energy equation can be combined into a complete plate or the beam or the shell case, and that shell case we can find the stiffness and the mass matrices, and those mass and the stiffness matrices by using that we can find the natural frequencies. That's what simply I am telling. And here I will use these MATLAB simulation for performing this finite element formulation of the analytical solution. So here this is the measured one with the experimentally, and these the finite element formulation results by using a MATLAB numerical simulation, and these the percentage of deviation for a various magnetic fields: 0, 75 Gauss, and 150 Gauss and 250 Gauss. So these are the various experimental results. So by seeing here, we can see the experimental results are matched with the analytical results. Gone for the various the influence of variation in the magnetic field on the natural frequencies with a fully treated. The fully treated means the complete composite plate core being replaced by a MR fluid. So then that is called as the fully treated. So this one is a various parametric studies. For this formulation, we took a size as a different. Normally 300 by 300 size plates are considered for here. And three different magnetic fields and five modes we have taken. And for various cases, fully treated, and this is the partially treated. The partially treated means here you can observe the complete MR is here, and whereas here only the MRF magnetoclassical fluid, and here one place only we kept a magnetic classical fluid. So I can just show you how this, yeah. So this is a complete plate where this is A in a mid position. This is 50 by 50. Normally this is 300 by 300, and this is 50 by 50. That we have divided this 100 by 100. Then we have divided these into 50 and 100, 50 and 100. Same thing. We kept in the horizontal direction, vertical direction. Then split up again into 25 into 100, 50, 100, 25, 100. Then 25, 100, 50, 100, 25, 100. Then it is like a 25, 25, 25, 25, like a four different patches used like A, B, C, D, E, F. So these are the partial treated laminated composite. Uh, what the need to go for a this partial treated is, normally these rheological or the viscoelastic materials will have a very high density. So due to this high density, the structure will become more weight. Once the structure becomes more weight, then we can know that mass is increasing. Once the mass increases, its natural frequency will goes down. So that's why we splitted these are the where there is a more need of a this particular rheological fluid or the rheological elastomer is needed. There we'll keep the elastomer or the fluid. So then the treatment is called the partial treatment. So we can observe various types of the partial treatments: A, B, C, D, E, F. This F is the one where we have these 100 by 100 cross 100 patch. We have divided into four different patches, like 25 cross 25. So that's why its property or its natural frequency is very high. So this one here, there is a lot of variation is there because of this splitage of a patches. It is only one patch, and this is a four different patches. Then obviously you can see a lot of difference here. So then these we can observe with a fully treated. So the fully treated natural frequency and then partial treated one with the same dimensions, but only thing is that here we can observe 44.26, this 130 to the 44, so almost like a 90 hertz difference is there. Due to this difference is because the mass increased here, and here the mass is reduced, but structure wise there is no change in the dimensions are the same, but only the core, the top and bottom face sheets are the same. Only the core, we completely these 300 by 300 across 300 is a MR fluid, but whereas here only we are using a 100 cross 100 that is split into again four different patches called as a 25 cross 25. There is four different patches. So like this way we can observe how by reducing the weight of a smart material, then we can increase its or we can enhance its properties. That's the major observation here. And if you see this composite one without using any smart material called the magnetoelastic fluid or the elastomer, obviously it can't sustain or it can't give this much natural frequencies and this much damping properties. So here one more thing is that we can increase its damping property also. So these are the various mode shapes for the clamped condition, all four sides clamped. And this is called as the 1 comma 1, and this normally this side is a 1, 2 comma 1, and there is a 3 comma 1 and 1 comma 2 and 2 comma 2, and it is called as the 3 comma 3. So that means 1 comma 1 means where the only one mode shape is there here for both the direction. This is y and this is x. For both the directions only one mode is there. So whereas here we can see there is a one mode here, and again another mode here, whether it is a positive or negative. These are the modes. So that's why you see 2 comma 1. So only one mode in this direction, whereas here they said only 2 modes are there. That's why it is called the 2 comma 1, and it is called 1 comma 1, and it is 3 comma, sorry, 3 comma 1. Then it is 1 comma 3. Sorry. Then it is called 2 comma 2. Then it is a 3 comma 3. It is a 3 comma 3. So like this way we can see these mode shapes here for this plate condition. Then this is about this partial treatment magnetic field. This magnetic field here in the partial one, will fix this magnetic field only to the particular distance where this patch is available. So for one patch we have done this. These are the test specimen, is a 50 by 300, whereas this patch is for the 150, and this MR field, and the remaining place we have covered with a rubber layer. And these are the 6 different combinations. Then these partial results also compared with the FEM formulation. So here also it got a very good agreement with the finite element formulation or the analytical results with the experimental. So these where we can check how its transverse vibrations can be reduced by applying a magnetic field. So red color one we can observe, this is G, and this is the displacement in the decibels. So with 100 and 250 we can observe here there is a reduction in the displacement are there, as well as some shifting of these excitation frequencies. So here this excitation frequency is more for the 250 cos, but whereas in the starting or the first natural frequencies there is no much improvement in the excitation frequency, but there is a displacement is reduced. But whereas once we go for the higher natural frequencies, the excitation frequency is also increasing, as well as its displacements are reducing. So from this we can clearly understand that by applying a magnetic field with a magnetorheological fluid sandwich beams on the plates, so here the reduction in the displacements are happening, as well as improvement in the excitation frequencies. Then next is the dynamic characterization of the tapered laminated composite sandwich magnetorheological fluids. So here in the previous case, a scene like a sandwich plate where there is a uniform configuration is there, and these uniform are normally used in these backside these the aircraft wings they will use, and whereas here in the turbine blades kind of thing, there is a tapered structures are needed. These tapered structures are the having a one brilliant property called as it can enhance or it can change its properties at one location to the another location. So these about the tapered one. So here once you see the tapered one, we can understand. So here it is more flexible, and here it will be a more rigid. So these variations in the properties according to the location or the geometry. So these are very good property. That's why the tapered configurations are needed, especially for a case of wings, where there is a turbine blades or the wings are there, or the sorry helicopter wings we'll use here. Uh, Whereas in the aircraft one wings will use a uniform one. There we can go for a uniform MRF or the MRE, and where there is a wings, there is more flapping action is there. There some flexibility should be there. Especially these this place is a or these structures are at a end. So at these end, there should be more flexibility should be there. So then only the material won't fail. If let us say at the end case, if it is not flexible, then it will crack or crack will be generated and it will fail very quickly. So that's why we need more the flexibility as well as the strength also, and as well as the stiffness also. These can be obtained by using this tapered configuration. Where in this tapered configuration, you want to make the same thing with by using a metals will be a more costly affair. But whereas we're using a composite material, we can fabricate this one. For fabrication of these composite tappers, we need what are the various types of the plies orientation, and as well as the ply distances, ply the locations or the ply positioning. So according to these ply positioning, we have the four different types of the tapered configuration. This is called the internal tapper, and it is the external tapper. External tapper you can understand here, where these internal tappers are the more efficient one compared with the external tapper. That's why we go with these internal tappers. There is a four different models. It's called the basic tapper, where all these here in this white one we can understand. These are the white one is a fibers, and these colors are a these are the matrix material. So these are the matrix material. Matrix combination or the matrix placing at only at the core, middle, and the remaining places there is no matrix. Then obviously these fibers cannot have a bonding. So that's why this basic tapper is not possible. As well as one more thing is only keeping here the matrix. So won't be a more strengthened member. So these member cannot withstand more loads. So that's why this basic tapper is not that much efficient model. So whereas the model B, the staircase arrangement, where it is like a in the middle will have a more uniform fibers, and then after that we can put these resin or a matrix patches. Then we can use the plies here. This is called the staircase arrangement, and these one model C is called the overlapping dropped plies. So here the short fibers at the inside in the tapered position only. That's why it's called overlapping dropped plies. These are the dropping plies. Then continuous plies interspersed. So these are the one where we'll have a one short fiber, then one long fiber. It will be uniform. Then again it will be bended. So like this way, it is the model D is a continuous splice interspersed. So these are the three different major configurations we considered for the fabrication of tapered composite sandwich, MRE sandwich. So these are the top composite layers, and these middle of the core layer, macrorheological elastomer. So here the macrorheological elastomer has been made with a silicon rubber. The silicon rubber based macrorheological elastomer has been made. So here 100 PHR, the silicon rubber, this weight parts per 100. So and iron particles are 40% iron particle. Each iron particle is having a 15 micron size and supplied by the Xi'an Taimu company, China, and dicomal peroxide with a 10 pHr, which will act like a hardener for the silicon rubber. And this combination, we have mixed composition was thoroughly mixed in the mixer mill, and after that passed through the rolling mill, so that we need a uniform plate structure. That's why we rolled this one, and for thorough mixing as well as to make this as a uniform one. and kept it in the mold. After you make this one as a we had one mold for the MRE mold. Then in that mold we kept these plates, MRE plates or the MRE sheet. Then these vulcanized using a dichomal curing at 120 degrees centigrade for 30 minutes time. Then we got finally 0.8 mm thickness, and there is a 350 length macrorheological elastomer sheet. So this sheet was used here, the core. Top layers and the bottom layers have been fabricated by us in the noise and vibration and acoustic noise vibration harshness laboratory in the VIT Vellore. And these are the three different configurations. We got these actually, and these are microelastic elastomer layer, and these tapered configuration second one, and these tapered configuration. So this is the model C, then this is the model B. Then experimental test we done. So here the magnetic field is measured by using a gas meter, and here the test specimen and magnetic bars. Then these are the Davisoft, and these are the results we can get from the Davisoft and tapered configuration. By using this hammer, we applied a initial forces. Then accelerometer, it took this acceleration reading and converted into a digital signal and displayed here. So for this, the testing specimen size test specimen. So from here to here, this is a 300 mm, and width is 50 thickness, 50 and thickness varies from the thin to the thick. So we got differently because this is thin one and this is the thick one. So here the single axis accelerometer is with a 105.08 MB by G and force hammer of 086 C03 and DAQ with a Q0442451 and permanent magnets of the south and north and south poles. And by using a gas meter, we measured magnetic fields by altering the distance between specimen to the magnetic magnets. So these are the 6 different mode shapes we received by taking these clamped free conditions. So here you can observe these x-axis, in the x-axis only one, and here and here you can observe 2 and there is a 1. So it's called 2 comma 1, and again 1 2 1 comma 2, and this is 2 comma 2, and there is a 3 comma 1, and it is a 1 comma 3. So like this way, 3 different mode shapes have got it. So here you can observe this mode shape. So like this way, here I have combined for the width and tapered configuration with only tapered plate and with sandwich. So that combination actually is the comparison of the first 6 free vibration modes with a symmetrically laminated uniform and the tapered plates. So uniform plate and the tapered plate with the clamped free specimen. So these one, the one with the uniform and another one with the tapered one. So this red color one is the uniform one, and this green color one is the tapered one. Then experimental results. These are 3 different configuration. Here again we did a analytical formulation using these composite and energy formulation, then apply the finite element. So here it took like a 4-noded quadratic element or the rectangular square element and 4 nodes, and various more shape functions, and after these shape functions we converted these energy equations in the form of the FEM, and then we found this K and M matrices for each element, and that is combined for total element. So then the total stiffness and the mass matrix we have received. From this we found the natural frequencies. Now here we consider the 7 degrees of, I consider the 7 degrees of freedom, and here the experimental results. So TSP1, TSP2, TSP3. So these mathematical formulation I will describe while here discussing about the MATLAB. And these are the percentage of the deviation. So you can observe the deviation will be more, or the normally it is more at the first natural frequency, and effect of magnetic field on the natural frequencies. So now I took a various parametric studies increasing its magnetic field and how the natural frequencies are increasing for all three different combinations of the three different. So TSP1, TSP2, TSP3 is called the first tapered configuration, second one, third tapered configuration. So 1, comma 1, the natural numbers and natural frequencies. And we can observe by increasing the magnetic field, obviously, there is a more increment in the natural frequencies also is happening. And when compared with the TSP1, TSP2, TSP3 will be the more stiffer number. But sometimes the TSP3 and 2 are basically almost got the some similar results. But finally, we can say that TSP3 is a more stiffer number, and effect of magnetic field on the loss factor. So how is loss factor? Loss factor is nothing but stored energy by the total strain energy. That will give us the how much energy is being stored by this number. This will this is one measurement for the damping characteristic of the particular structure. So here we can observe where there is a less natural frequencies are there. Obviously, there is a more damping is occurring here with the TSP2. So that's how we can see the loss factor value. Loss factor is also increasing by increasing the magnetic field. That means the damping characteristics of that this structure is also improving a lot by increasing the magnetic field. Again, there is a configuration variation. Your TSP1, TSP2, TSP3, all that three tapered configuration is having the same size and the same type of the MRE, but still there is a more property perspective. One configuration is giving more damping values and the more natural frequency values. There is a variation is there. These variation can be attributed only to the structure or the configuration or the geometry, not for the material property. So material property perspective, all are same only. Then here the transverse vibration response of a tapered MRE sandwich plate by with a three different magnitudes. So 0 gas and 1000 gas and the 2000 gas. Here we can see there is improvement in a excitation frequencies also, and a slight reduction in the displacement velocities. So then we'll see these partial treatment. Partial treatment is one is the more advantageous in the two cases because we don't need MRE or the MRF throughout the structure. So we need the structure only at a particular location where there is a more flapping action or the more reduction in the vibration. So there only we need that one. So in that case, no need to apply these MRE or the MRF throughout the structure. So we can use this one at only at a one particular location in the form of a patches. That patches we already see there is 6 patches are there. The same 6 patches have been considered here, and for the three different tapered configuration. That's why this is given as a PMC called the partially treated MRE tapered composite sandwich plates structure. PMC1, PMC2, PMC3, and for the ply orientation, there is a 90 degree and 0 degree there is a 2s. So obviously we got a 8 number of plies for each configuration. We can see here also we have a 8 plies in the top and 8 plies in the bottom. So these are experimental setup available in the noise and vibration harshness laboratory, EAT Vellore. And for only for the partially treated case, permanent magnets are used where there is a only applied magnetic field applied only for particular patch location. And these results are compared with the FEM results, the finite element formulation results. So here we can observe there is a less deviation. This deviation is within the reasonable limit. You can say that FEM formulation and the experimental results both are agreement. So this transverse vibration of the PMC at 3 different magnetic fields. So here also we can observe by increasing the magnetic field, the excitation frequency is also drifted towards higher side, as well as the transverse responses are reduced with by increasing the magnetic. So from these we can understand the natural frequencies are increased. So that means stiffness is more. Once the stiffness is more, the transverse responses or the amplitudes also reduced. And we observed there is a damping also increased. So what are the various applications of these magnetoreological fluids? So these are the various operation modes with the pressure we applied, pressure in this direction and applied magnetic field in the opposite direction. So this is called the flow mode, and here it is a direct shear mode. So the magnetic field is applied in this direction, forces are applying in this direction. So this is called the direct shear mode. And this is the one where magnetic field is applied in the same direction and the force is also applied in the same direction. This is called the squeeze mode. Then we can use this MR damper with a semi-active control, okay, with a MR fluid dampers. So here the current drives and MR dampers, the controlled damping forces, the force transducers, the plant and the disturbance is out. So this sensing can see what is the needed, whether the damper is controlling exactly or within the our controlled or estimated one. So that will be checked by this output sensor and intimated to the controller. The system control measures this one, and what the difference is there, that difference one will be given by the damper and it will give the signal again. So if it is okay, then directly it will go here. But whereas when there is some modification is needed, then it will go to the controller and it will immediately alter its damping ability. So like that way, the MR dampers with a semi-active control. So here is the closed control loop system is there used. So here by using the magnetoreological elastomers, we are doing, that's why it's called the semi-active one. Then the MR damper operated in the mixed mode condition. So here we can see the mixed mode condition here we can observe. So the uh, flow mode and then the shear mode and squeeze mode. So here we have a both combinations. Okay, this mixed mode combination of the flow mode as well as the direct shear mode. So both are there. Here we are applying the force in the opposite direction. So these the opposite direction, magnetic field is applied in this direction. So obviously there is a flow is also needed. Then there is a direct shear is also happening. So here it is the magnetic field and force is applying in this direction, and it's moving in this direction. So this how we can apply the flow mode and the direct shear mode. This application of MR macrorheological elastomers. So here the active damping compensated MRE. So these are the adaptive toned vibration absorbers. So by using these absorbers, this is schematic representation and is the photograph of a this active tuned vibration absorber. So these are magnetic conductor, then these are voice coil, then MRE, and it is the magnetic field, and this is the coil. So this is a vertical guidance. Once we need the absorption, so obviously the magnetic field will be enhanced. So according to the requirement, so that way its vibrations can be absorbed. Then this is the soft macrorheological elastomer, as it is new actuator. So here we can actuate these MRE by applying the so this is the airflow and it is the mechanical support. This is the MRE ring and this is the closable gap. So these are the loops. These are the solenoid valves. And once this sufficient flow is happening, then obviously these solenoid valves will give a signal to the MRE. Then obviously this gap will be filled. And if want, it can the gap can be increased. So like that way, we can flow can be controlled. This is about the experimental setup for the MRE ring in the center tube. The frequency tuned electromagnetic energy harvesting using the is the energy harvester. There is it beam, and this is the tip magnet, and this is the energy conversion coil. So this is the MR elastomer with the tuning magnets, and this is the motion direction. Then we can see here the angle bracket and these tip magnets. So this is the energy conversion coil where this energy can be stored. So this is the block and the photograph of this experimental setup where laser Doppler vibrometer is there here used. So to measure what is this uh, oscillating motions and how much of its velocities and all can be measured by using this vibrometer, laser Doppler vibrometer. And majorly Doppler vibrometers will be used for the rotation purposes in a non-contact type. So this is a function generator and this is the oscilloscope. So how much FFT signals will be generated here, and here we can see these direct signals, and this is about the shaker. So with the shaker only, how much energy is can be harvested by using this frequency tunable electromagnetic energy harvester. Then MRE bushing for this automotive application by applying a magnetic field, then obviously increases stiffness. Where this bushing can be done, and these bush can run for the long time. These are the coils, so that whenever you want to be more stiffer, and then bushing can be rigid, and then bushing can be a normal by applying a magnetic field. In this way, we can control its properties. Any question and answer just before? These are the faculty members associated with this vibration lab, advanced vibration lab, also called as the noise vibration harshness laboratory. Uh, Dr. R. Vasudevan, Professor and Dean, School of Mechanical Engineering, Ganapati, M. Professor M. Ganapati, Professor SMEs, School of Mechanical Engineering, VAT, Professor R. Manoharan, School of Mechanical Engineering, and Professor Mallikarjun Reddy, and Professor Ramesh Babu, Professor Edwin Sudhakar, and Professor Sridhar. We are the faculty associated with the Noise Vibration Harshness Laboratory in the Vellore Institute of Technology, VAT. So these are the references of the MRE, and these are the references for the MRE. Thank you. Any question and answers you can ask. Hello, can you able to see this one? PPT. Hello,
Hello. Any queries with
madam.
the participants?
Somebody has raised a hand, madam. Please check it.
Oh, okay, so I'll just have to unmute them. I'll unmute them. Participants, can you unmute themselves? Participants can unmute and ask the question. Hello. So I think no queries.
Okay. Okay, madam.
Okay. So just a minute. So with this we come to
Thank
the
you. Thank you, all of you.
thank you, sir. With this we come to the end of session one of today, and afternoon we'll be having a session at 2 o'clock. The link will be shared at 2 o'clock only for the 2 o'clock session. So kindly log in and you may please wait for the link. The feedback link will be shared for the 2 o'clock session. It will be common. And also the quiz link will be shared by today evening. So you people have to attempt a quiz. I request everyone to please make sure that you are attempting the quiz to receive the certificate. A quiz will be conducted till Saturday, sir. Thank you very much, Ravinder Garu. Yes, sir. So Ramesh, sir, thank you very much for your time and your valuable session, sir. Hello.
Yes, madam. Thank you, madam.
Yes, sir. Sir, we will meet at 2 o'clock again for a hands-on session on MATLAB.
Yes, madam. Definitely.
Yes, sir. Thank you very much, sir. So for the information of the participants, The feedback link will be shared in the afternoon session, and the quiz link will be shared by today end of the day in the WhatsApp group. I hope everyone is there in the WhatsApp group. If not, please log in or please ping me. I'll send you the link. My number is 9966 100 434. You can ping me on WhatsApp so that I can send you the quiz link. That is the WhatsApp group link I will send you. If you are not, if anyone of you are using the WhatsApp. Thank you and see you all at 2 o'clock in the afternoon.
Ma'am, feedback link
So feedback link I'm telling you, sir, I'll post it in the afternoon session. Same
posted in.
afternoon session.
Acha, not for this session.
For this session also in the afternoon. Again, you'll be logging in. No? That time you can give a combined feedback. I
Okay,
have
okay,
taken the screenshots.
okay, okay. Thank you.
Assignment is quiz you have to attempt. So today, end of the day, you will be receiving the quiz link. So it will be open till tomorrow morning. You can attend the quiz anytime, and the quiz will be on the topics discussed in this week. Around 20 questions will be there.